Okay, good morning. Welcome to the fifth and final day of our virtual summer school. Today, we're going to do some exploration that is more science-y, less about the tooling, but you'll still be learning how to use some of the tools, doing some sort of basic science explorations. Before we get into that, I just wanted to take a minute to thank the organizing committee and the Rubin Community Science team for all of their work. So many of you have done a lot of work making this what I hope has been a successful week for everybody. So thank you very much, everyone. Otherwise, I don't have many announcements. I do hope that many of you will continue to stay involved in Data Preview Zero activities. We have DP0 delegate assemblies every other Friday, and then on the Fridays in between, we have what's called Stack Club. The delegate assemblies are, we usually have a presentation, sometimes from a DP0 delegate, sometimes from a Rubin staff person in the first hour, and then the second hour we go into breakouts where you can work collaboratively with your colleagues. Stack Club is 2 hours of just hacking together on projects, and so those both happen Friday mornings, my time, Pacific time. So it's 9 to 11 Pacific time each Friday. So I encourage you all to attend if you're at all interested. It's a great place to learn from your colleagues and develop projects together. And I think that's all I have for announcements today. So today we are going to learn about extracting and working with light curves of variable stars from Vincenzo. So you can go ahead and take it away, Vincenzo.
Thank you, Jeff. Okay, going to share my screen. Can you see the screen?
Yes.
Just 1 minute. Okay, yes, I was also taking the chat window so that I can say if there is something happening. Okay, so welcome everyone to this last day of this summer school. And today, as Jeff said, we will use all the tools and all the techniques that we learned during the first 4 days to do something more science-oriented. And so the notebook of today's session is tutorial 7B, variable star light curves. And I also suggest you to make a copy of this notebook to your own directory, because the directory of all the tutorial notebooks is read-only, so it's better if you have a copy on your own workspace in a different directory. So is it big enough?
It's good for me.
Okay, thank you. So the container size suggests that for this notebook is medium. So yeah, I will zoom a little bit. So if you have a medium notebook, should be fine. You should not have problems. And so I have to say that for this notebook, we have to thank you, the authors. So primarily Jeff Carlin, and also the contribution by Bob Habel and Ryan Lau, who modified this notebook recently. And so the notebook is about understanding how to do science with other light stars, so how to measure the period using a Lomsdal periodogram, and also how to select candidate of possible other light stars using the information that are provided into the Rubin tables. So we will use all the things that you already learned, so top tables to do query, and we will also do some joint merges between multiple tables and extract light curves. And so let's start with the notebook. So this is an introduction to all the details and all the tables that are available. So the first thing that you have to do when you want to extract a light curve, you want to look at the time series, is to go to the object table, because the object table is the one containing the unique object identifier for each astronomical source that has been detected by Rubin. But if you want to have multiple entries for the same object, which is important if you want to extract the light curve, you need to go to the source table or to the force source table. And the difference between the two is that the force source table has all the entries, even if the signal to noise ratio is below the threshold, which is 5 by definition. And the other difference is the table with the difference image analysis, these ones, and they have this DIA in front of the name, and it is exactly the same thing. So the DIA object table is the table containing unique entries for all the sources that have been detected on different images, while for the DIA source table, you have multiple entries for the same object, but you have the same unique identifier, which is the DIA object ID. So I know that this may be confusing at the beginning, so one thing that may be helpful for you, and I will put this into the chat, is this big document, like 70-page document, which is the official data product definition documents. I don't know if there is a more recent version of it, but where is the chat? I just missed the chat. Oh, here it is. But in this document, we have all the information about the data products. So if you try to scroll down a little bit, maybe something that we can discuss in one of the breakouts later. So you have the differences between the prompt data release and the annual data release, information about all the tables, and also a brief explanation of the pipeline, so how the pipeline is working. So I think it's an important document to have always with you if you want to understand what to do with LSST. So I saw a message in the chat. So it seems that you cannot open the document. I don't know, Jeff, do you know why?
I had to log in.
Okay.
I was able to, once I logged into DocuShare, then I was able to see it.
Okay. Yeah, maybe you have to log in. I don't know. We can discuss later about it, because usually you just have to write on Google Rubin data products, and you should find this file. It's strange. So, okay. So I will go ahead with the tutorial. So the first cell is quite straightforward. You're just importing the typical packages that you use. So there is NumPy, Matplotlib, and AstroPy. And in particular here, we are importing this thing from AstroPy, which allow you to execute the LOMS-Gargle periodogram. And then, of course, the top service to do queries. Then there is this other cell. This is an optional cell. You don't have to execute it. It's just to define some parameters that you want for plotting. And if you don't execute this cell, you will just have the default parameters of Matplotlib, but you can modify the number so that you can have plots that looks good for you. And then there is also this cell, which is quite similar. You are just defining the labels for the different filters and colors associated to different filters. But again, if you don't execute this cell, you will just have the default colors for different filters. And this is just to have the same colors that are usually used for these publications. So the first important cells start with this. You executed, initialize the top service to do queries. And so the first thing that we will do in this notebook, the notebook is divided into two parts. In the first part, we will use coordinates of a star that we already know is a simulated error Lyre. And then in the second part, we will use all the tools that we test with this single object, and we will apply them to a sample of possible candidate error Lyre star. So as a first thing, we know that there is an error Lyre with these coordinates. in degrees. So what we know is to go to the object table and get the unique object ID for a star with this coordinate. And then we will go to the force source table, querying for multiple visits, so to get the photometry for the object with this object ID. So first thing that we do is to define two variables with the coordinate of the star. And then we go and actually execute the query. So the query is very similar to the queries that we launched during the first days. And so there is top 100 to limit the number of sources that you can have. But actually here we are just trying to get one object. And so if you go here, you can say that we are imposing the query in a very small radius. So it is 0.001, because we just want to get an object which is likely the objects that we are looking at. And all the parameters that we are using for the query, we are also querying for the extendedness parameter, because we want to be sure that we are having an object which is compact, so it is a star. So if you run the query, so it is the typical query, you have select with all the things that you need, you have from for the table and where for the conditions. You can save the result of the query to a table, and you can plot the result, and you can see table length equals 1, because in this very, very small search area, we got just one object. So we are happy because this is probably the object that we are looking for. And if you scroll down the table, you can see that it is an object with magnitude around 18. And the extendedness parameter is 0, which means that it is a compact object. So it is probably a star. So we can go ahead, and now we can get the thing that we actually need, which is this, the object ID, because we need this ID to go to force source table to extract the photometry. So we define a variable with the object ID like this. So this is the name that we gave to the table. 0 is to say that we want the first row of the table. In this case, we just have one row. And then there is this other parenthesis where we put the name of the column we are interested in, which is object ID. You can say it is this one. So we saved the ID into a variable, and we can also print it to see that everything is okay. And then you have this thing, which is the object ID that you are interested in to query for the photometry. So now we have all the ingredients that we need to get actually the light curves. So we can make a query to the force source table. The resulting query is this one. The only thing that you need to have in mind while making a query to force source table is that you don't have information about time in this kind of table. And so we are making a join, and I think that this was also presented yesterday by Ryan in the notebook about supernovae. So that is the select with all the information that you want to query. Then from, you have the first table, which is this one, force source table, and you are adding this nickname, SRC, so that you can easily define if the variable that you want to query belong to this table or to another table. And then you have join, and this is to put two different tables together. And the second table that you want to call in is this one, CCD visit. And we are using this nickname, this info, to refer to this table. And then if you want to make a join, while you're making a query, you need a condition for this join. And the condition, you can express it with this on. So you have on, this info is referring to the second table. And you want that the CCD visit ID, which is present in the second table, is exactly the same CCD visit ID, which is present in the first table. And you can see that you always have the nickname referring to a table, then you have a dot, and then you have the name of the variable which is present in the table. And this is a very common thing in relational databases, as the database of Rubin, where you have usually a common keys between different tables that can help you to do merge and join between different tables. So we can now run this thing, run this query, and actually this is not executing the query, it is just saving the string of the query into this variable. And you are querying for the bands, the visit ID, the fluxes. You are converting fluxes to magnitude using this function that we also saw yesterday. And again, to know what things you need and what is present in every table, you can take a look to the schema browser. So this is a very friendly thing that you can just read to understand what to query and what is present in all the tables. Once you define the query, and in the query, the unique condition that we are imposing in this one with where. So we are imposing that the object ID into the first source table is exactly equal to the selected object ID that we defined before by doing the query on the object table. So what we expect here is to have multiple entries, but all the entries that are related to different visits with different filters are associated with the single object, which is the single star that we are looking at. So to execute the query, we have this cell, so service.search, and then there is the string containing all the information about the query. And then we save the result to a table. And we are also printing the length of the table. And you can see that it has more than 400 entries. And these are all the visits at all the filters related to this object. Are there any questions up to now? Is it clear? I hope it is. You can also print the table to see how it looks like. And it is like this. So this is the length of the table. And you can easily look at the bands. So this is the first column. So this is the R band, but you also have the I band. We have all the available bands in LSST. And these are all the other things that we queried. So the coordinates, the fluxes, the magnitude, and so on. So this is what you need if you want to plot a lat curve. But of course, the first thing that you need now is to find an easy way to divide between the different bands, because you want to plot the lat curve separately in principle. So there are many ways of doing it. What you can do is using this kind of approach, defining an empty dictionary that we call pick. Then we do a for loop on all the filters, and we just append the entries according to the different band. So if you try to print this thing, you can see is that it is like a mask. So it is for the U band, you have a mask array, which is false if it is not related to the U band, and true if it is related to the U band. And it is the same thing if you go to the G band and to all the other bands. So I'm going to comment this because we don't need it. And now you can plot the lat curve. So as an example, we will plot for the R band. And the way to plot the lat curve is using matplotlib. And so you define the figure, and then you have plt.plot. The first argument of this function is the x-axis. And so it is the name of the table. We define it like this, SRCS. Then we use this dictionary to refer to the bands that we are looking at. So it is peak and it is R because we want the R band. And then we have this other thing to refer to the actual column in the table that you want. And this is for the time. Then we do exactly the same thing for the y-axis. But we are using PSF mag because we want the magnitude. So I saw a question in the chat referred to error bars. And yes, you in principle can plot the error bars, but I think that we did not query for the errors. Let me see again. No, we did not. But yeah, maybe later I can show you how to do it with the error bars. We are not doing it now because we don't want to make a confusion into the plots, because we will put all the bands together. But you can query for error bars, and then you can just use plt.error bar, I think, and you just have other two arguments into the function for the error bars. You can show later how to do it. So we run this command, and what we expect is to have the light curve for the error band, just points without error bars. And this is the result. So it might be a bit confusing, but if you look carefully at it, you can see that there is almost 1 magnitude deviation from the minimum to the maximum. And it may seem kind of periodic. So, but of course, like looking at the light curve like this is not so immediate. So what we want to do now to test that this is actually an error Larry, or in general a periodic source, is to do some analysis with a periodogram to study the periodicity. And so this is what we are going to do right now. So we want to create a phase light curve. And so to do it, we use the Lomscar package from AstroPy, which is allowing you to define a periodogram. And now the Lomscar periodogram is actually a slightly modified version of the traditional periodogram that may be more helpful where you have gappy data and not evenly sampled light curve. So you can just click here. And if you click here, you have all the information about this package. So you also have some examples explaining you how to run it. And so what you expect is something like this. So for a periodic source, you may expect that you see how the power is going as a function of frequency. And then if the source is periodic, you have a peak at a specific frequency, which is the period of the variable source. So we may expect to find something similar for another Larry. So if you go again here, so the first thing that we need to do is to separate all the observation related to different filters. So in this way, we can easily deal with different filters. And so we define two empty dictionary, one with the days, so with time, and the other one with the magnitude. And so we do a for loop. So with the first for loop, we are appending all the times related to a specific filter, and even times in day. And in the second one, we are appending all the magnitude, the PSF magnitude for the specific filter. So this way we have everything separated, and it is more easy to deal with that. After we have this, we can actually try to measure the frequency using the periodogram. So now we know that this is an error line for the simulation. So we know that we expect a period between 0.2 and 0.9 days. So what we can do is to delimit the minimum and maximum period that we expect, like this, 0.05 to 1.05 in days. And so, but we are working with frequencies, so you have to remember that frequency is the reverse of the period. So it is 1 over the maximum period and 1 over the minimum period to define the edges of the frequency range. So we run it. And then finally, we are going to run the Lomscar function from AstroPy. So what we do is to define, again, empty dictionary for frequency and power. And so we do a loop on all the filters that we have. And for each filter, we define frequency and power with the Lomscar periodogram. So as an input, you just have to put the time information, the magnitude information, and then you can use the auto power with the minimum and the maximum frequency where you expect to have something, where you want to study your source. So we can run it. Okay. It's pretty fast. Now, as I showed you before, if this is a periodic source, you may expect that there is just one peak at the frequency where the period actually is. So what we can do is to define the position of the maximum in frequency for all the filters, and we can try to understand if this position, if the maximum frequency is the same for all the filters. So what we do in this cell is to define an empty list which contain all the peak frequency. And so for each filter, we define the position of the maximum. And then we also say both the magnitude and that position and the frequency. And we also measure what is the mean frequency and the mean period, which is the 1 over frequency over the bands. And so the final result is like this. So we have a mean frequency of this, and the period is corresponding to 0.5 days. And if you look at the result for all the bands, it is like this. So you can see that actually the frequency is practically the same all over the available bands, and it is consistent with the mean frequency that we are getting. So now we have this information, and with this information we can plot the periodogram. So we can plot the power as a function of frequency, and we can also plot the power as a function of time. So this must show you the effect of having a distribution with the peak exactly in the frequency of the maximum. So if I run this cell, so it is just the typical matplotlib thing. So you have frequency, you have power, and we are doing this for the R band. And this is the same thing, but for the second plot, instead of frequency, we are plotting time. And this is the final result. And you can see that this red dashed line is identifying the position of the maximum that we find, and the position is actually the same position of the maximum of this distribution. Now, maybe it's not so clear, but you can modify the transparency of the red lines. So using the alpha parameter, which by default is 1, if you put like 0.4, now you can easily see that there is a peak around this frequency, and this peak is corresponding to this period, so 0.05 in days. So it seems like a well-behaved periodic source. So it seems that we can build a phase light curve, so we can define the phase using the period information. So we define the best period, which is 1 over the mean frequency that we define. And now we can define the phase. So to define the phase, what we do is a kind of normalization of the light curve. So as an instance, we do it for the G band. We have to define a starting point. The starting point is completely arbitrary because this is a persistent source, it's always present. So as an easy thing, we define T0, the starting point, to be the first G band observation, but you can do whatever you think it's useful. And so the phase time are just the time information minus T0, and you divide everything with the best period. Then to define the phase, we use this mod function of numpy because we only want the non-integer part with the last period. So we want everything to be between 0 and 1 because we want a phase. So if you run this, and then if you go it for all the bands, and you try to separate all the bands by imposing an offset, which is this I equals 0, and then this in this loop, I is increasing. So you can plot the phase for each filter, the magnitude, and on the y-axis, instead of having magnitude, you have the magnitude minus the average magnitude, and then you're adding an offset if you're moving to a different filter. and you can plot everything together in the same plot, you can have something like this. So now on the x-axis, you have the phase, which is between 0 and 1. You have the mean value, this gray dotted line, and on the y-axis, you have magnitude minus mean value of magnitude, and then there is the offset so that you can look at the different light curve together. And this is a good result because it actually looked like an error light, even if I'm not an expert of this, but it looked like a periodic source, and there is a very well-defined period. You can also try to put everything together on the same plot. You just have to run exactly the same cell, but without the offset. And this is done here with this cell. This is exactly the same thing. So you have the phase on the x-axis, everything into a for loop because we want to do it for all the filters. And on the y-axis, you have magnitude minus the mean value of the magnitude, but this time with no offset. You run it again, and now you have the phased light curve of your other light year with all the points with no offset on the same plot. So with this couple of cells, we defined a framework which may be useful to study a lot of stars together. So it's one of the first scientific applications that we are doing using DP0 data. Are there questions so far with this first half of the notebook? Okay, so it seems everything is clear, or maybe the opposite, nothing is clear. I hope the first one. So what we are going to do now that we define this kind of framework using a star that we already know was another Lyrae, is to do something similar to what Brian showed us yesterday. So we are going to start from the available tables, and we are trying to select possible candidates, other Lyrae stars, applying the same tools that we applied now to just one object to more objects. So we are going to make very long, complicated queries, but now I hope that everything is clear after this 4 days of school. So what we want to do now is going and look at the DIA tables, so tables of sources selected on different images. And this is because these tables should also contain information about periodic sources, variable sources, not just transient, because these are variable. And so unless you're looking at the point where the variability is just starting with respect to the template, you should observe some variations. So if you go to the DIA object table, you should have detection for all kinds of variable sources, not just for transients. And then you may go and look for the DIA source table to extract the photometry. But the only caveat about these different images is the threshold or the signal to noise ratio, because with this table, you will just have the detections with signal to noise greater than 5 on different images. And so, of course, for a variable source, a periodic source, this depends on the phase, depends on the period of the observation. So you may miss a lot of visits if you just look at this table. While if you look at the first source table, you have all the detections. So we will see how the light curve is changing according to which tables are you looking at. But we will also see how to identify candidate variable stars. So it is written here in the DIA object table, and you can also see it if you go to the schema browser. You have a series of indicators of variability. And it is expected that with the actual survey will start, we will have even more of these indicators. And a list of all these things is in this document here that I can put in the chat, because these are all the time series features which are expected to be provided by Rubin when the survey will start. And there are features both related to periodic sources and non-periodic sources. So it will be extremely important to have a first test of all the objects. What we have here are a couple of things. So an important indicator is the StatsOnJ statistic, which is based on this paper here. And it is an indicator where high values are indicating that the flux of our source is varying more than it is expected. So typically for variable stars, you expect that this StatsOnJ index is greater than 20. So now this is a very naive query, and of course, experts working on this field may define more accurate parameters, but this is just an indication of what you can do using the information that is provided already in the tables. And other things that you may use to make a query is an information related to the scattering fluxes. So you may ask that the ratio between the uncertainty, so the scattering, the flux measurement, and the average value is greater than a certain threshold. So an idea could be to have 25% greater than mean. Another thing that you can do is also to define a range in the average magnitude. So we will limit all the analysis here just with the G band, but we can put a limit where you expect to find these sources. You can put another constraint on the minimum number of data that you expect. And so here, the idea is to have at least 30 observations. And this because we are not looking for transient, we are looking for persistent sources. And so if you have more observation, it is more likely that you are not taking into account transient that are disappearing at a certain fraction of time. And then there is the index that I was mentioning before, that it is typically an index used to define variable stars. So what we can do now is to make a big query, selecting all the information that we need to do the analysis that we did before with just one stars, imposing a lot of these constraints and looking both of the DIA object table because we need the unique identifier and on the first source table because we need the photometry. So this is probably the biggest query of this summer school, but I hope it's not scaring you. But we will try to look at this query to explain all the passages. So the first thing that I suggest to you is to focus on the things that are written in uppercase. So the first thing is select, and it is containing a lot of information. We can skip it up to now. Then there is from, which is another important thing because it is giving information about where to look for the information. And if you go here, there is where, and where is for the conditions that you are applying to the query. So in this part, you are basically just translating in ADQL language what I told you before about the condition that you want to the query. So this is a rather complex query because it is actually using 3 tables. So here you have 2 join. This is because the first table that you are querying is the DIA object table. And you are referring to this table with this nickname, DIAO. Then you are joining this table with the first source on DIA object table because we want the photometry. So at a certain point, you have to get all the information, all the visits, all the fluxes measured for the single DIA object that are present in this table. And the condition is that the DIA object ID that is present on the first source table is exactly the same as the DIA object ID that is present on the object table. And then you have another join, and this other join is because there is no time information on the first source photometry table. And so you are calling again the CCD visits table, and the condition is that this common key is the same. So the CCD visit ID, which is present on the CCD visit table, is the same as the one that is present on the for source table. And it is extremely important to look at all the nicknames that we give to the table, because when you go to select, you have to provide information not only on the actual column that you want to query, but also on the table containing this column. And so that's why you have dia.dia object ID, and the same thing for the coordinates and all the things. But if you go down, you have also this thing. So this is the object ID, but it is present on the for source photometry table. And then you have also this thing, this is the time, but this is present on the CCD visit info table. So it is extremely important to have the information about the table containing all the information. So it is a long query because you are getting information about the coordinates, the fluxes. This is the minimum and the maximum flux because we were imposing the condition about the variability on the sources. Then there are this thing to convert the fluxes in nanoJANSP to magnitude. And we are also querying for the stats on J index and for the percentile of the fluxes. So it is containing a lot of information, and all the constraints start here with where. And so it is what it is written as a words here, but it's written now in the ADQL format. So yeah, that this ratio must be greater than 0.5. Then this other ratio must be lower than 1.25. And it is important that the things that are present in the condition, I think they must be parameters that you are querying, otherwise you may have an error. And then the last one is just to limit the search in a smaller area, otherwise you will have a lot of sources, because you have to remind that it's 300 square degrees, the simulation. So it's better just to limit in a smaller area. So again, now we are going to execute this query. And I think that this is also one of the examples that if you copy the query, if you paste it in the portal aspect, you're going to get exactly the same result. And maybe it is easier if you just want to interactively look at the light codes without doing this kind of job on the notebook. So we have all the information here. We save the result, the table in this variable here. If you comment this cell, you can see what's happening, what is the result. But before doing it, I think it's a good habit to try to understand how big the table is. And so if you go here, we can print the length of the table to understand how many entries we have. And with this other thing, you print how many unique DIE object IDs you have. Now, the different thing with this kind of query compared to the thing that we did before is that now we are doing everything together. So you are not querying the object and then you are going to the for source table to get the photometry. You are doing everything together. So if you run it, you see that you have more than 700 entries, and these are related to different filters and different visits on the same object, but the unique objects, so the unique object ID are just 14. So the result of this query are 14 candidate other light stars and 700 visits in general. So now, in principle, yeah, you can try to do it. You expect to have a big table, but looking at the table like this, it's not so easy to understand what to do. And I think that what is important is to try to study just single objects and understand what are the coordinates, what are the average properties, and to do a first test with these objects. So a question in the chat?
Oh yeah, Vincenzo, I just made a comment in the chat about, I think I was the one who wrote that super long query. And then as you're going through it, I think, and I went through it yesterday as well in a demonstration. And I think, maybe it would have been better to break it up into two separate queries that might demonstrate what's being done a bit better. But I thought you did a great job at breaking it down. So yeah, just a thought.
I think if you are a beginner, it's better to separate different queries in smaller pieces. This is a more advanced thing, but you already know what you want to do and you just put everything together. Yep, thank you. Okay, so what I was saying, we have the information about the number of objects because it is 14 objects. So let's start by plotting the object ID and the coordinates of these objects. And we are going to do it in this cell. So this is the name of the table. So the key is the object ID because we want just the unique identifiers, and the variable that you want are this object ID and the coordinate. If you are interested to something different, you can also add another variable. Maybe you want the average magnitude, may be important. So the result is this. The table length is 14, which is what we expect. And you have the coordinates related to these objects. Now, there is a warning here, an important note. This is something that the community science team is actually working at. There might be problems in the association. And so it might be that the single source may be associated to multiple DAE object ID. And this is happening here with these two sources. If I go up here, yeah, you can see it. It is the second and the third one. You can see exactly the same coordinates associated to two different object ID. So that's why it's always important to check this thing, because they may seem like easy things, but if you don't check them, you may have more sources that are actually present. So now it is important to check this thing because it may happen. So what are we going to do in this cell is to run, again, in a very brief and synthetic way, the same thing that we did with the single star, because we are going to do the Lomskargol frequency analysis, but now on all the candidates. So we do it here and we save the result into those lists, and we just make a for loop on all the object ID of the object ID table. So the result now, I can try to print it, should be just a list with all the values. Yes, exactly. So this is for power, and this is for frequency. Just save the result into lists. Now you can try to plot the light curves of all these candidates. I remind you that we just queried for the G band. And in this cell, we are just selecting 3 light curves as a test. And these are the object ID related to these 3 light curves. And this is very similar to the cell that has been showed in the previous part of this notebook. So we will just run it. And what we have as a result are the phased light curve for these objects. Now, we don't know if these are actually error-lining. So we are just imposing some possible cuts on the entire data set that we are trying to understand by doing the Lomskargol analysis if this might be error-lining. So this is the result for the first one. This is the second one. And this is the third one of this example. Now, it seems that at least one of them seems a striking periodic source. What I want to show now is that you can do exactly the same thing, but instead of doing the query to extract the photometry from the force source table, you can just use the DIA source table. And there is an advertisement here, so you have to be careful about what you do. And that's because what I said before. So there is the limiting signal to noise ratio to have sources detected here. And so as it is a periodic source, it will not be observed always, especially close to the magnitude value of the template image that have been used. So you expect to have less visit in the DIA source table. But we can run the query anyway. So this is again very long, but it is exactly the same query as before. And the only difference is that it is using the DIA source table instead of the force source table. And there is just one join because now the time information is already present. So we run the query again. And if you want to print the length of the table, you can see that again, you have 14 objects, but now the total length is 549, which is less than 700. So it is something that you expect. So what it might be useful now is to plot for the three sources that I showed you before, the light curve, both using the photometry extracted from the DIA source table and the photometry extracted from the force source table. So with this set, again, we are doing the Lomskargol analysis. We select exactly the same sources and we plot the light curves. So now you have two different symbols. The open triangles are related to the DIA source table, while the filled one are related to the force source table. And of course, you can say that there are less open triangles because you have less visits. It's not always the case. It was not the case in the previous one, but this is the case in this one. For sure, you don't have more. This is the only thing that you should have. And this is for the other one. So you start to see differences in the retrieved phases. And this is an important thing to keep in mind if you want to do science. So maybe this is exactly the kind of things that it might be important to discuss in one of the breakout, because now is where the experience of the users is jumping in. Users that work on this field know what to expect and know all the possible biases. What you can try to see is that what is the fraction of sources that have different periods measured using one of the other tables. And it seems like for this analysis, 70% of the identified catalogs have different periods that have been measured. And you can also try to plot the distributions of the absolute difference in the period measured from the two tables. The result is like this. So only 5 of the 14 candidates have period date change by less than 1 hour. So it seems like it is better to use the force source table when you are trying to study for persistent sources like variable sources in general and not for transient, because you might have biases for the sources, for the visits that you are missing, because the magnitude is close to the magnitude of the template that is being used for the subtraction. So from this kind of analysis, it seems that the difference image analysis is good to detect sources, but maybe when you want to do science, it seems better to look at the force photometry to have all the observations. Then in the last part, there are suggestions for exercises for the learner. So you may try to experience different way to do this kind of analysis. Also refine the selection criteria, both using the one that will be provided for the future data releases, the actual data releases of the survey, or defining your own things to select possible candidates. I think that's all. So if you have questions, we can try to discuss. But any question?
Yeah, so Vincenzo, we're having a discussion on the chat. So there was a comment from George Ree about the precision at which the coordinates are listed and what the actual I guess, accuracy in the coordinates is, or what the uncertainties on the coordinates are. So I wonder if you have any thoughts on that.
The precision of the coordinates. So you're referring to this, right?
Yeah, I think that's right. And yeah, it seems, there's several significant figures after the decimal point. So we're wondering, like, what is the actual uncertainty on this, and what precision would be good to.
I don't have the exact answer to that, but I think that it is written in the data product definition document that I attached to the chat at the beginning of the notebook, because there are all the information related to the pipeline and to the uncertainties. I don't remember now what is the uncertainty about the coordinates. Yeah, of course, it will depend on source brightness, so not easy to provide an easy number. But I think there are documents referring to these things more carefully.
Okay, yeah, that's a good point. Thanks.
And also related to the earlier question about magnitude errors, I tested it out on that bright star that we were looking at, and if you actually extract the magnitude errors and overplot them, they're smaller than the size of the data points on that, because it's such a bright star that they're just tiny errors.
Yeah.
Any more questions for Vincenzo? Well, thanks so much, Vincenzo. That was great, and there's a lot to dive into if you're interested in more detail. There's a lot to look into in that notebook. So now we'll take a quick break for 10 minutes. We'll come back at 10 after the hour, and then Douglas will show you how to one of the benefits of using a synthetic data set is that you know the truth information. And so Douglas is going to show you how to put together the measurements from the catalogs generated by the pipelines with the truth tables in the next demo. So back in 10 minutes. Okay, welcome back, everybody. Let's get to the next tutorial, which, as I mentioned before the break, is going to be about how to access and work with the truth tables underlying, telling us about what went into the simulations. So I'll let Douglas take it away.
All right. Well, thanks, Jeff. 1 second here. Need to find my tab.
Well, you're still muted though, Douglas.
Oh, I am?
Oh, maybe not. Maybe no, it's just me.
Okay.
Sorry.
Okay. All right. Yeah. So, okay. Share screen here. Okay, and people can see my screen?
Yes.
Great, great. And I will open up the chat so I can see that. Okay, I'm actually going to do this a little bit differently. So there's a lot going on with the truth tables, and so I'll go relatively quickly through this notebook, but I want to show a couple of things from delegate contributions about the truth notebooks, just to give you a flavor of what can be done with the truth notebooks. Let us start out with notebook 8, and then I will.
Douglas?
Yes.
Sorry to bother you. Can you minimize your sidebar and then up your font a little?
Minimize my sidebar. Oh, yes, I can do that.
Thank you.
Yeah, I guess I can entirely minimize that. Okay, does that look good? Okay, great. Okay.
Thank you, sir.
Oh, no problem. Okay, so as Jeff mentioned before the break, one of the benefits of using a simulated data is that you know that you have we know what went into the simulation. We have catalogs of objects that were simulated and put into the images. The images were basically originally blank, and then you did stuck things were injected into the raw images, and then they were processed. And so now you can go see how well you can actually compare the original inputs to what came out after after simulation being processed and coming out of the data processing of these images. And in fact, there's actually a lot of things that go in, which are if we have time, we'll see later, that are too faint to actually be detected by Rubin. They just tend to be kind of noise, and we'll sort of see that. We may see that too if we get to one of the contributed notebooks. But anyway, here we're going to see how we can access these truth tables. And now there's also a caveat here. So the Dark Energy Science Collaboration generated these, and some of the we don't necessarily have all the truth tables that are that might be that all the truth information that went into the simulations. These are sort of somewhat of a subset, because it's kind of unfeasible to do but everything, everything that kind of went into the simulations. So there are some limits to what we can do here, but we'll show you what is available. So I'm actually gonna, since we go through this, we went through this many times now. I think we're all familiar with a lot of the introductory stuff about doing imports and setting special things. So I'm just going to zoom through this and go to section. Basically, go to section 3. But you do need to kind of run through things to get the information that go into section 3. It's like we're going to grab results about what's in there, but we're more or less I'm going to just let you let you do this mostly on your own. Let's see. Oh, it should mention. Let's see. This is one. So the matches. It's the matches truth table that in the DC2 that we are looking for. And it has an ID as a truth type, a match candidate, whether it's matched to something that was identified in the processed image, how good the match is, how many candidate objects were matched, and the truth type. So we have like 1 for galaxies, 2 for stars, point sources, and so on. But 2 for stars, 3 for supernovae. Oh yeah, so I guess this is a very important aspect. The match ID, it's matched just to the object table ID. So that's one limitation that I'll try to show you a little bit later in another notebook, that you have to match. There's only the match to the COAD object ID, not to other things. So you either have to do maybe triple joins in your SQL search, or you might have to do your own matching to some extent if you're doing like a DIA object. But we'll look at that a little bit later if we have time. But I guess the primary thing is what we're probably mostly interested in is the match ID, the object ID, and the truth type. Okay, well, but yeah, I guess you can look at the schema for there's also a truth summary table, which is also important, and you have the summary you have a summary of what went into the truth. You have the match, which tells you what things are, where the matches are between the process data and the original inputs, and you also have the information that went into the original input information. And we can you can just do the normal stuff of looking through things, whether it's a point source, is a variable with some magnitude and R band, the redshift, and the fluxes with and without Milky Way extinction, and so on. Okay, so here we'll get to the meat of the matter. We want to retrieve the truth data, and we'll join the matches truth table. Basically, okay, I should slow down. I'm kind of going very fast here. Here I should slow down. Okay. So we have these two important tables from that provide truth matches to the original inputs. So we have the matches truth table, as I mentioned before. This tells you what for each it tells you the ID of the that connects the true summary table and an object in the process data in the processed object table. So from the COAD, so you have an object in the COAD, and the matches truth table tells you what that connects to in the true summary table. And so here, so as described in the column description above, we're looking for the ID truth type. The column ID truth type should be used to join the matches truth and the true summary table. So here we do a selection. We grab from the so let's see, we are grabbing things from these two tables, the true summary, and we're matched actually the true summary and the and the matches truth table. So matches truth, we're calling M, or just giving a symbol. We're giving an alias of MT, and truth summary, we're giving it an alias of TS, just for simplicity. So we're matching those, and we are looking for things within. In this case, we are grabbing. We're finding objects which have a true RA deck within 0.1 degree of more or less the center of the simulation. That's what's happening here, and we are grabbing the truth type, the match to the thing in the object table. It's true RA and true deck, and it's truth type. And that we've created and then we can look at the results there. So here we have a lot of things which are not which have no matches. And we have the ARIA deck, and we have the truth type. So so here is the ID and the ID combined with the truth type. So it's ID underscore the truth type. These are all galaxies. The truth type of 1, because there's mostly galaxies in the simulation. So let's see. Notice that not all objects in the truth table have matches in the object table of detections in the deep co-edited images. In other words, the match object ID is blank, meaning there was no match. There's a lot more things. So there's literally a lot more things in the simulated data than there are in the input to the simulations than there are detected in the images, because the simulation extends out very to large redshifts and faint magnitudes basically below the detection limit of we're looking at things like magnitude 30 or something, which are not which is a couple of magnitudes deeper than what would be in that would be detected in the COAD in the COAD images. So here we'll just print the fraction of retrieved truth objects that are actually matched to the object table. And so we create basically a mask using a NumPy. We've got the array of objects where the match object ID, that's this column, is greater than 1. And we'll print that out. And then we will divide it by the total number of results, and we'll round it to 2 decimal points. So the total number is so the number of objects number of matched objects are about in this 0.1 degree radius circle is almost 15,000 objects, and the fraction of truth objects that are matched to an actual object is about a quarter, about 0.23. So that gives you a rough idea of what's the amount of inputs that go into the simulation, and how many would actually be detected, because most of them, a good 3/4 of them are below the detection limit. All right, let's delete that. Now we get to the joy of doing triple joins, which is always kind of scary. So let's actually match it to the actual object. Let's look at the object, some object information. So here we match we use the truth table, the truth summary table, which gives you the information about the what went into the simulation. We have the objects table, which has the detected objects that were after processing the images and doing the detection algorithm and deblending and so on, and the matches truth table, which connects the two. So here, here we will select the ID truth type, the object ID, the true summary RA and DEC, and the true summary truth type. Okay, these are all from the truth table or from the match truth table or the true summary table. And then here is sort of like the real stuff, what we've actually detected, quote real, because these are all of course simulated data, but after processing the images, we grab the ARIA deck. And so we select from the matches truth table and we do a join of that on ID truth, which is in both those tables. That's the connector. That's really the connector between the two tables is this ID truth type. So so when you have two tables and you have one column in each, which is basically the denotes which rows go with which rows. Is you join on that row, that you join on that column, or you join on that column, and then we also do an additional join using on the object table. So these are on object ID. So we have the match object ID from the match truth table and the object ID. That's the running ID in the object table. And once again, we're looking at things within a circle that's roughly at the center of the simulated data and 0.1 degree in radius. So that's what this where clause does. This is sort of study just that one area. So we'll run that and we'll kind of twiddle our thumbs for a moment or maybe 2 moments. And actually, while it's running, any questions? I know I'm going a little bit quickly here, but I'm just trying to give you more of a flavor of what's going on. Star galaxy classification. Yes. So of course, in the truth table, we know beforehand what's a star and what's a galaxy because there's a because they have a catalog of stars and a catalog of galaxies, and you can actually so we'll be able to, we won't do it here, but we can verify how good the star galaxy classification is in our processing by comparing what we know is a star or a galaxy based upon the truth table, and compare what we got out from the processing. Okay, so here we have we got some information out. We have the ID, the truth ID plus, and appended to that is the truth. There are, of course, galaxies, and actually in this case, all we see here are galaxies. There are stars in there, but we don't see them right here. We have the object ID of the match, and the R and DEC from the truth table. And okay, here's the truth type, which is also appended to the ID truth here. These are all galaxies, and the R and DEC. So that was just we do, however, okay, that was just a brief example, but we does lead into this point about efficiency, and I won't go into the detail of this because I don't understand it myself all that well, but the different tables, the DP0 tables are stored in one way in the QServe database that we're querying with the TAP server, differently than how the matches truth table is stored, and there's some efficiencies involved when you do queries. So you could actually, depending on how you do the query, you could actually have it go much. It can actually take much longer if you don't query correct on the faster mode of faster the table that's most quickly queried. So there. Oops, okay, that's much larger than I wanted it to go. Max, it's always hard to control things. They always want to do what they want to do. So we just have a caveat here that if your query is running a lot longer than maybe a few minutes, you may want to contact someone, community forum, a GitHub issue, or the DP0 RSP services issue of the community forum. And there are people much more knowledgeable about this than I am. Could tell, maybe help you tweak the queries for optimal execution. So there is that resource. You can ask people via the community forum for help with your queries. So let's see. Going through that, we will. Okay, we're looking at a single object here. We're going to look at for a single object. So let's see. Here's querying for a single object. Yeah. So here's what. Yeah. So this is the warning was. So we can do that. It's not, and we can find out for this object. It runs very quickly, but if you change that, the join, if you switch these, the on and the joining and what you're joining on, if you flip those, it can take much longer. So just a warning there. Okay. Moving on. Let's see. Retrieve additional galaxy for true galaxies that are matched to detected objects. Okay, we will. So let's do this. You all have seen these queries before. But basically, we're doing another one of these triple joins to grab so we can match some object information. Basically, this is the extendedness, RA deck and extendedness. And actually, this is kind of refers a little bit to what George was asking here we are sort of looking at how well the extendedness measure matches with the true. So actually, this is sort of address star galaxy separation here, and we'll also grab the R-band C model mag, and also the other filters, the fluxes of the other filters. And we'll do one of those triple joins, and once again just grab that little area, that 0.1 degree radius area around the center of the DP0 area, and we'll just grab things which are truth type 1, which are galaxies, and things which in the object table are listed as primary, that they are they're not children of other, that they do not have any children themselves, or that they have to be blending. These are the final objects, the final primary objects. So it's a big long query. Okay, we'll run that, and I'll also set that going here. This will probably take a few, maybe, I don't know, hopefully not more than a minute. And I will kind of stop for a second and ask if there are any questions. Oh, and let's see. I see on the chat, Bob mentions if it's a galaxy. Actually, it's a comment, a very good comment. I kind of brushed aside that there are many. So in the processing, many different types of magnitudes are used, so you may want to use, say, PSF magnitudes for point sources. For galaxies, C model magnitudes are a good choice. or these, and where the C, as Paul points out, and I had not remembered, stands for composite model. Oh yes, so that's a very good comment. Thank you, Bob. Are there other questions? All right, this is taking a little bit longer. Has anyone been keeping up and finished gotten the result back yet? Okay, yes.
2 minutes, 16 seconds.
Okay. All right, so here's where we do the thumb twiddling a little bit. I can say a few words. Actually, I will kind of jump ahead a little bit while we're doing this. We will be looking a little bit at some stuff from the delegate contributions, DP0, if we finish in the next few minutes with this tutorial notebook. So I'll add this into the, I think we've mentioned this before, but we do have there's a GitHub repository for all these things. The tutorial notebooks are also here. We have delegate contributions for DP02. We also have some old ones from DP01. Things much even older things from what was called the Stack Club. It's still, and we still have the Stack Club that meets every alternate Fridays, and you're all welcome to attend those. And actually encouraged to attend those. These are working meetings. And another nice thing is there's like little demos. I think we've mentioned those a little bit earlier. Little short informal demos of different things, which not quite enough to make into a tutorial, but show useful things. We haven't quite filled those up yet. We're starting to add things as time goes by. So let's see, has my thing finished? It has finished running. How about that? Okay. Let's see if I can readjust my screen here. It's one of these Mac things. I always forget kind of have to use 2 fingers on your, okay. I'm not sure if I'm gonna get that. I want to stay on the page. Okay, we'll have to deal with this as is, I think, for the moment. Okay, so we have a nice table of the ID from the truth table with the truth type appended, the value of the match in the object table, the object ID from the object table. It's true summary array and deck. It's true type. It's magnitude, and you see some of these are pretty faint. They're 27.5 or so. Those these are matches still. These are still matches. So these actually, so you can see that with the co-added data, you can get down, or we're getting down. Supposedly, these could also be mismatches down to about 27th magnitude. Let's see. TS, is it a point source? Hopefully it's generally it shouldn't be, because we've selected galaxies. The redshift, the true redshift, it's true fluxes in nanojanskis, the array and deck from the object table, and here is the extendedness. So 1 equals it's an extended object, and 0 means it was measured in the processing as a extended as a point source. 0 means it was measured as a point source. 1 means it was measured as a extended source. I think there's discussion of these right now are basically binary, 0 or 1. I think there's some discussion of eventually making in future releases making that into more of a range. So you have more of a probability as opposed to a plus or minus, and a yes or no in the data, in the process data. You have the object magnitude, the object fluxes. So that we can play with it. We can play with this data, and we will So usually after each section, we've been deleting the results, but here we want to use those in the next data so we do not delete the results. So now let's plot up some of these results. So here we are plotting the difference between the true and measured declination versus the difference between the true and measured right ascension, the RA. So, and this is in arc seconds. So you get a nice blob at 0, 0, which is good. And you get a extended tail. So that looks quite reasonably well. It looks like most things are within about 0.1 arc seconds, which is good. So let's see, for the simulated LSSD camera, the plate scale is 0.2 arc seconds per pixel, and that's basically what the real camera will be also. So that's so that's a measurement accuracy of about 2.5 pixels. This scatter of less than 0.5 arc seconds. So we're measuring. So most of the objects are measured as sub-pixel accuracy, which is good. Okay, and here we come to sort of getting closer to what George had asked earlier about star galaxy separation. Okay, how many true galaxies are measured as point sources? And we actually get about 19% are measured as of true galaxies are measured as point sources, but they are really faint and really small. So that is and with flux limit samples, the first order, everything is at the flux limit. If you're looking at out of magnitude of 20 R band of magnitude 27, the vast majority of your detections are going to be around 26 or 27. So, and they're going to be really small. So it's not surprising that there's a fraction that are actually measured as point sources by the processing software. So as it says here, for very small or very distant galaxies, kind of appears point-like, even if they were simulated as extended objects. And it's left as the exercise for the learner to explore what types of galaxies are measured to be point-like. So that's up to you guys. All right, so okay, let's compare let's look at the true versus measured R band magnitude. And so I won't go into detail of the plot. We've seen this all before. So some variation of it before. You can look at it again. So and so here we actually separate the ones which are measured as extended and as point-like, as different colors. You have the red, the reddish symbols are extended, and the black ones are point-like, and we have the one-to-one line going, the equality line going diagonally through this. So looks fairly good. We can do more detail doing delta mag versus mag, but that will be left for the learner. Okay, we compare the true and measured fluxes in all filters. So here we're just looking at the R band, but we can also look at for all the different flux, all the different measurements of the flux. And okay, we didn't discover these the magnitude, so it's sort of flipped. You see, yeah, basically that they get fuzzy when you have due to Poisson statistics as you get to fainter light levels, but generally it looks okay. Okay, now we can also look at compare the color magnitude diagrams for true and measured properties of the true galaxies. Okay, let's see what's here. There'll be a runtime warning because of some of the measured fluxes in the denominator being 0, but we'll just kind of ignore that. So we can plot that. So here's the true magnitude versus the true color, and here's the measured colored versus here's basically the true color magnitude diagram and the observed, and you notice that we get some extension beyond the outside the we get some basically garbage measurements outside. Basically, we're looking at things which are very faint, so that's not entirely unexpected. Do we have any? Does it say anything about here? No, it doesn't really. We don't go into much explanation here. But yeah, basically they're very faint things. So so it's not surprising that you get the overall shape is fine, but you get some outliers with bad measurements. And then let's look at some other plots. I minus Z. Okay, yeah, you're probably gonna get things. Yeah, you get basically the same thing. The main features in the center, especially for things which are brighter, matches very well. But when you get down into below a certain magnitude limit, things start to get bad, which is expected. You're getting close to the flux limit of the sample. And okay, that is it for this notebook. But I do want to show a few things from one or two other things from the delegate assembly, and we don't have a lot of time, so I'll just briefly go through those. But I just want to see any questions at this point. All right. Okay, I am now going to go to I'm not sure if people have downloaded the delegate contributions, but if I'll put this back in the chat window. So this is so in the GitHub section for the Rubin DP0 area on GitHub, you'll want to go to the delegate contributions, and you'll want to, if you do not have it yourself, you'll want to go to the green button and copy. You might use the HTTPS or the SSH, whichever. Either should work. If one doesn't work, you might want to try the other one. But then you'll go to let's see, where I've got. Oh, can someone remind me how I get the I mean, that's it.
In
No.
the file menu, you can then where it says new, that pops up a thing where you can get to the terminal there.
Okay, all right, yeah.
There you go.
I forgot how to get the. Okay, yeah. So we want a terminal, and you'll want to get close. Well, let's see. You want to go to the directory that you want to put things in. So say, I don't know if you have a directory somewhere that you like to stick your Git stuff in. You can go there and do git clone and what you grabbed. And yeah, actually be useful if I can grab that. Oh, here it is. No, that's not quite what I'm looking for. Here we are. Yeah, okay. So okay, so here we have in my case, I put it in my work area, and we will take a quick look at the desk truth. Okay, and we'll look at the read truth parquet. Are people, is anyone not caught up? I'm sorry, going a little bit quickly. Or have access to already had delegate contributions already downloaded. It's good too. Okay, I will go here. So not all, there are some additional truth tables that are available, but they are not available in the TAP service. They've been provided as parquet tables in the file structure of the RS key on data.lcc.cloud. So so these have additional information on, say, variability. For those who are interested in variable objects. I will find these quite useful, but you need to know how to read in a parquet table. Parquet tables are basically like, okay, for those who use FITS tables, FITS binary tables, they're sort of like that, but more so. They are very good for keeping lots of data in binary format and fast uploads. They were not made for astronomy uses in particular, but they're just generally file structures that can handle lots of data that were developed outside of astronomy, but are useful for astronomy. We will note that there's no cross matches. So people are using DIA object to try to match to these truth tables. You don't have that here. Okay, another issue here. Okay, you may, okay, some of these tables are very big. You may, and we're going to use something called DAS, which is like pan is for really big files. So you might want to restart your server, but we only have a few minutes, so I'd say let's not restart server, but I'll just show you what's going on, and later on maybe in the breakouts we can do this. I believe I already have using the large container size. I won't go into that here. So I'll just quickly show we import packages, including this Pi Arrow and data frame, Dask data frame package. And okay, we'll look at some stars. And so we have a summary table, which is just for each star, each variable star, it's just the mean characteristics. And then you have the variability table, which has all the variations as the star varies. We will read the summary table using this pandas read parquet command. You take a quick look at what's in there. You have the ID, RA, the fluxes, the model type, what sort of variable it is. I think we show that a little bit later. Yeah, we show that a little bit later. The maximum deviation and magnitude between its highest and lowest, the maximum standard deviation of the delta mag, to get an idea of how much it's varying. I think here it gets truncated. It's probably like 0.001 or something like that. So it's not showing that. And whether it's above the detection threshold, above a good detection threshold, you have the absorption, the galactic absorption in V band, and the galactic dust redding model, the RV model value for dust redding that was used to redden that object in the final column. We can identify, let's see, we use NumPy unique to figure out how many different variables type stars there are. So we'll kind of query on that that model thing, we're basically queried on model here, and we get 4 different types. We have there are Lyris and Cephians. There are non-periodic transients and variables such as microlensing events, flaring M dwarfs, cataclysmic variables, and so on. And there are basically there's sort of no definitive variability classes. Variability is modeled after Kepler light curves. So these are basically like transiting exoplanets. And then we have non-variable stars. So here we'll just we'll look at there's 211 of the Leary's type. So we'll just grab those here using a NumPy mask and print out. Let's see. Let's see. Let's see actually what's going on here. I guess we just I think we just printed out this the one of the objects. So we use TX to find all the 11, but we just grab the 0th one, the first one in the list. So you can look at more of them. If we could have queried a little bit more. Here we'll look at one in particular, which is admittedly was pre-chosen to have a nice result. There's a star at RA of 72.58 and minus 4464 that we'll grab. So we found its match in the table. Okay, so we can find out, we can find stars that way, and then you can use this pi arrow technique to grab the true light curve of this object. So we'll read it. We have to be careful. Okay, we grabbed the ID here. I mean, we can just read in that one item from the parquet table, so we're not reading the full table, which is good because it's a huge table. So we'll read that in. It takes a few seconds, so it's a big table. And then we will create it. We'll read it into a pandas data frame, and then we can take a quick look there. So we have, okay, all the ID is the summary truth from the ID is the same because we chose one star, and we have the MJD, the modified Julian date, the time of the observation, and the filters, and the delta flux from the average in nanojanskys. So then we can plot the fluxes. Let's see, do we convert them? No, we do not. Does not look like we convert them to magnitudes. And you get this mess here in delta flux in nanojanskys versus time. So, and then you can zoom in on a given area and see and see the one phase, maybe a given phase of the light curve. Let's delete that for now, and now we can use DASK. DASK is sort of like DASK is sort of like pandas, but for large data sets. So we'll kind of skip over this because we have like 1 minute left. But we can quickly go through and plot things with DASK. And okay, we're running out of time. I'll just very quickly run through supernova and see what we get here. Oh, as a timing function, that means it's going to take no. Oh, here it is. Oh no, here. Okay, we have a supernova and different filters. So that's nice. And you can also use DASK to do similar. And hopefully that'll take. Okay, so yeah, I can do DASK also. And then I will just briefly mention with the 0 minutes that we have left. There is another table in the DIA exploration. There's another notebook in the DIA exploration, which describes how to do matching on your own, doing RA cross table matching on RA deck on your own, since these have not, all these things, the truth tables have not been pre-matched. So it uses a technique in AstroPy. Where is that? Where tables, retrieve all table match. There is something there's something called Match Coordinate Sky that's available in AstroPy that finds the nearest match in a reference catalog to another catalog. It does, and the nearest match could be very distant, so it's like a nearest neighbor thing. So you may need to clip on things that you can match things and analyze the match. And I guess we could maybe, for those who are interested, we can maybe go over this in a breakout room. And I believe that is it. I would so this is the last last notebook, last tutorial in the summer school. All of us would like to thank Jeff for his amazing work over this time. I do not see how he has managed to maintain verticality through all this. It's been a very long week, and he's done a lot of things. It's been very impressive, and the members of the CS team would just want to thank him for all his efforts, and let's all give him so applause virtually or whatever, and you'll be at the sprint week in a couple weeks, Jeff, or no?
I will indeed.
I think we will. We owe you at least a drink, if not more, if not more. So thank you very much for leading us, and I'll and I also like to thank Ryan, who reminded me that this is the last session, so we probably should say something. So Ryan Lau, thank you for reminding me to mention this. And yes, thanks once again, Jeff, and I will stop sharing screen, and it's all off. I hand the baton back to you.
Well, thank you all for helping to organize everything and making everything run smoothly. And thank everyone who's been attending this week. I think everything has gone really great, and I hope you feel the same. Let's take a few minutes break, and then we'll come back and do some breakouts. So we'll just stick to our schedule and come back at 10 minutes after the hour. So enjoy a short break. See you soon.